Hello, pre-calculus students, and welcome to our continuing lesson on rational zeros and the rational zeros theorem, which is a method that we're going to use here to help us solve and factor polynomials of higher order degrees. Okay, and I just want to recap what we've been doing here before we move on, because this is essential that you see the big picture that we're working with. So first, zeros of higher order polynomials are difficult to solve. If it's quadratic, if it's a degree of 2 or lower, we can use the quadratic formula. We have a number of methods that we have at our disposal, completing the square, factoring, and so on. Graphing really helps to solve them, but it's not exact, and it's also, it fails for complex solutions. Okay, we'll deal with that later, but this is the main reason right now, is that it's not exact, and later on we'll see that for complex solutions it just simply does not work. And then from the last couple videos we've seen here, we can find zeros algebraically, but we need to be given a factor as a starting point. So we can find zeros of this function here. We can factor it down to something that looks like this, but to do that we really need to have something here as a starting point. Otherwise we can't factor it. Okay? So what we're going to focus on today is we are going to find a way to make a good guess for a starting point. So imagine we had to do this problem up here, but we weren't given this extra bit of information. What we're going to learn about today is how do we get that, how do we figure out where this term here comes from to even have us as a starting point. Okay. And so I'm going to introduce an important theorem today. This is called the rational zeros theorem. And this is what it says. It says if f of x is a polynomial of this form, a sub n x to the nth power plus a sub n minus 1 x to the n minus 1, so on and so forth, all the way to a sub 0. And this is just a very precise way of writing a polynomial, but all you really need to focus on for right now is that this is the leading term or the leading coefficient, and this right here is the constant. Okay. If there are any rational zeros, so this theorem is saying that all of the rational zeros, if any exist, are fractions of factors of a sub 0 over a sub n plus or minus. Okay. And this theorem is just is a somewhat complicated theorem in the way that it's stated, but when you see a couple of examples, it'll be very, very straightforward. Okay, and so with that in mind, let's take a look right away at an example. Okay, so here we have a function f of x equals 2x to the third plus 6x squared plus 13x minus 8. We want to list out all of the potential rational zeros. So rational zeros may or may not exist, but if they exist, they have to take this form. And the key word here is they're factors of this. Okay. So we're going to look at the leading coefficient, which is 2. Okay. So that's a sub n is equal to 2. The constant, which is negative 8, a sub 0 equals to negative 8. Okay. And then we're going to list out all of the factors. So you got to think back to elementary school. What are all the factors of 8? Well, there's 1, 2, 4, and 8. And what about all the factors of 2? Well, there's 1 and 2. Okay. And so the potential rational zeros, and the key word here is potential and rational. Potential means that it may or may not be. So it could be, but it also could not be. We don't know yet. but it's a good starting point for us. And rational means that it's a fraction. Okay, rational is basically P over Q, where P and Q are both integers. Okay. So to find the rational zeros, this is what we do. We fix one of the factors for the leading coefficient, and we divide all of the factors for the constant. So one of the factors could be 1 over 1, plus or minus, of course, 2 over 1, plus or minus, 4 over 1, plus or minus, and 8 over 1, plus or minus. Then we fix the next factor of the leading term. Now it could be 1 over 2, 2 over 2, 4 over 2, and 8 over 2. Okay. And so some of these you can see are duplicates here. So 1 over 1, that's plus or minus 1, 2 over 2, plus or minus 2, 4 over 1, plus or minus 4, 8 over 1, plus or minus 8, plus or minus 1/2. 2 over 2 is just 1, we already got that covered. 4 over 2 is 2, already got that covered. And 8 over 2 is 4, so we already got that covered. So these here are the potential rational zeros. Okay? So if there are rational zeros, they're going to be one of these numbers right here. Now, not all of these are going to be zeros, but some of them may be. And so one way to check this is that we can actually plug these numbers in here and seeing if we get a 0 out of it. That may take a while. So let me just show you using a calculator here how we can actually use the calculator just to quickly check these. So you can take out your TI-83, TI-84 graphing calculator. I'm just going to type in this function, 2x to the third plus 6x squared plus 13x minus 8. And I don't know which one of these are potential zeros, so I have to check all of them, but I can use my graphing calculator here to help me. You can see here the biggest potential zero is -8 or +8, so that's going to help me with my x window. So I'm going to go, this is perfectly fine from -10 to 10 because I'm covering all of these. Hit graph. And you might not see a complete picture of this, but you can see that it crosses the x-axis somewhere, and you can make a really good estimate. And it looks like it crosses at negative, or it's positive 1/2. So we can actually test this. Hit trace, 0.5. Okay, so that wasn't it. Okay. And maybe is it 1? Well, that isn't it either. So it looks like, and I'm trying all these other zeros here. It looks like there are no rational zeros here. So these are the potential rational zeros, but the actual function has no actual zeros. Okay, so we checked. So these are potential rational zeros. But then we checked with calculator, and there are no rational zeros. Okay. And that's okay. So in this case, we know then that when we're dealing with this function, we have to use a graphing calculator to solve this, because there is no good algebraic method. We can't find a potential rational zero here from looking from this list that actually matches an actual rational zero. Okay. And which is okay. So in math, that's perfectly fine. We have a good list to check from here, and sometimes our check doesn't work. nothing wrong with that. Now, the good news is that a lot of times it will work, and it will make the problem much simpler, much easier for us to solve. Okay, so the main thing I wanted you to get from this video here is how to produce this list, okay, and then check it. And if it doesn't, this particular problem here doesn't actually give you a real rational zero, that's okay. We know how to find a potential list, and in many other examples, this will be useful for us. Okay, so I'm going to end this video here. I'm going to pick up the next video where we actually use this method to completely factor and find all the zeros.